there's an important concept in Bayesian games called signaling, which is where information which is hidden by the game becomes revealed, or in some cases partially revealed by the moves that players make. Um, so that is to say, information which the rules of the game do not reveal, but are revealed after Bayesian updating given the strategies. This follows from the general principle, which continues to hold in game theory, that players behave as though all strategies are known. So when a player's strategy reveals information, the other players kind of learn it because they know what the strategy is doing and they know what the strategy would have done in other states. So let's see this. I'm using another very kind of economic example rather than an AI example, I'm afraid. But so the market for lemons is actually my favorite example in game theory. So this is a game where player one is the seller, is selling a used car, and player two is the buyer. And the car is either good quality or it's a lemon, I should say bad quality. So the seller knows if the car is good or if it's a lemon. So we're going to model this as a type for player one. Now the seller, and then the seller, after observing whether the car is good or a lemon, can choose to charge a high or a low price. The buyer is going to observe the price that's offered, but is not going to observe the type. And then the buyer has to choose to either buy or not buy. We have, I think I've written this wrongly in the slides. The payoffs are set up so that, this is right. So things are set up so that in both types, both for a good quality car and a lemon, the buyer values the car higher than the seller, which means that trade for mutual gain is theoretically possible. Okay, so we're going to set this up where we have two types for player one, which is good and lemon, and then we have one type for player two, which I'll just call star. This is kind of a dummy type that says player two always has this type. So here is this game as an extensive form tree. So we have two types for player one, which are good with probability mu and lemon with probability 1 minus mu. So the seller is going to observe this and is going to choose low price or high price in both states. Now the buyer, so I've set up information sets for the buyer so that they always can see the price, but they can't see the type, and they have to choose to buy or not buy. And there's a bunch of numbers here, and I haven't written the formulas that are used to calculate these numbers. That's the kind of more details of the economic side of the model. But these come from kind of subjective valuations of the value of the car. And there are two possibilities here where there is possibility of trade for mutual gain, where both players get positive payoffs. One is where a good quality car is sold at high price, and another one where a lemon is sold at low price. Both of these lead to trade for mutual gain. The other possibilities, so if there is no trade, payoffs are zero, and there are two other possibilities where either the seller or the buyer is ripped off. So if a good car is bought at low price, then the seller is ripped off. If a lemon is bought at high price, then the buyer is ripped off. Okay, and I haven't written this here. The possible prices, the high price is 110, the low price is 60. This just comes from the details of the model. So 110 means high price, 60 means low price. So a reasonable strategy for player one is to play this strategy that plays high price for a good quality car and low price for a lemon. So that means charge a price that is appropriate for the quality. Now, notice that if player one uses this strategy and player two knows that they're using the strategy, then this completely reveals the type to player two, even though player two in the game doesn't observe the type directly. So that is to say, the posterior probability that the posterior probability that the type is good, given that the move is 110, is 1, and the posterior probability that it's a lemon, given that it's 110, is 0. And then similarly, the posterior probability that it's a lemon, given that the price is 60, is also 1. So this is called signaling, when after Bayesian updating, the player learns new information that they didn't know before, and they learn it perfectly here. Now, the consequence of this is that if player 2 is using a strategy that acts on the information that's revealed in the signal, then suddenly something genuinely new happens that we couldn't talk about in game theory before, which is that player 1 suddenly has incentive to switch to a deceptive strategy. That is to say, to kind of missignal. So let's see this. The kind of obvious good pair of strategies that would lead to the best possible outcome is that player 1 will charge a high price for good quality and a low price for a lemon, and player 2 will always buy. This is the strategy profile that will always lead to trade for mutual gain, but it is not a Bayesian Nash equilibrium. The reason is that because player 2 plays a strategy that will always buy, player 1 has incentive to always charge the higher price unilaterally. And you can think of this as, because player 2, the player 2 strategy to always buy is a good strategy because player 1 is signaling the type. But when player 1 deviates to charging a higher price, this is a deceptive signal that a lemon is high quality. So by charging a higher price for a lemon, player 1 is essentially lying within the context that player 2 is interpreting the signal. Okay. Here's another thing that we could do. So let's see if we can kind of repair this strategy profile to see if we can find an equilibrium. So suppose player 1 sticks to the same signaling strategy, but player 2 will not buy at a high price, but will buy at a low price. So that means that kind of we think of player 2's goal is to buy lemons cheaply and not bothering with good cars. But now player 2 would like to deviate. So because player 1 is signaling the type, it means that player 2 would like to deviate to buying a high price, because high price is signaling the quality. So in this case, signaling is a kind of a barrier to strategy profiles being Bayesian Nash equilibria. So there are equilibria where player 1 always charges a high price. These are non-signaling strategies for player 1. And then whether player 2 buys or not will depend on their prior belief. There are some details here. So what happens depends on the probability mu. So mu was the prior probability that the car is good, and then 1 minus mu is the probability that it's a lemon. So we can think of this as the common knowledge that a certain proportion of cars in the market are good. So if we set mu to be 1/5, 20%, that means that this is a kind of low. This means that the market is flooded with lemons. So in this case, it's a Bayesian Nash equilibrium that player 1 will always charge the high price and player 2 will never buy. So that is to say, there is no trade in equilibrium. On the other hand, if we increase mu, the prior probability, if we increase it, say, as far as 11/12, so now this means that most cars in the market are good. The prior probability of a lemon is low. So now, in this case, it becomes a Bayesian Nash equilibrium. Instead, the player 1 will always charge the high price and player 2 will always buy. So what's happening here is player 1 is not signaling. Their strategy is not revealing anything about their private knowledge of the type. And then what the buyer does is basically what's rational for the buyer to do is determined by their prior belief. Because player 1 is not signaling, they don't learn any new information, so they have to go by their prior belief. And so that means essentially that what happens in the game is not enough to overcome not enough to overcome player two's initial belief about what the state is.